right, welcome everybody. Today we're going to be talking about electron configuration. So when Bohr did his experiments, we've already talked about how he used light to determine that energy levels exist within the electron cloud. And Bohr wasn't wrong. To this day, we still see the electron cloud divided up into energy levels. However, later on, scientists using the Schrödinger equation determined that each energy level is further divided into sublevels. Okay? Each sublevel is made up of one or more orbitals, and each orbital will hold up to 2 electrons each. So here are the different types of sublevels that exist within each energy level. To explain this, I'm going to kind of draw a Bohr model over here. And we've looked a lot at the Bohr model, and it's something you should be familiar with because you discussed it in middle school. We know that each ring represents an energy level, and we probably already even know that the first energy level holds 2 electrons, the second one holds 8 electrons, then 18, and finally 32. But we probably haven't talked about why that is. So when we're looking at sublevels, the first energy level really only has one sublevel, and that is the S sublevel. The S sublevel only has one orbital. And we already said that each orbital will hold 2 electrons. So one orbital times 2 electrons equals 2 electrons total in that S sublevel. And the first energy level only has an S sublevel, so it only contains 2 electrons. The second energy level, however, is larger. And since it's larger, it has an S sublevel. Every energy level has an S sublevel. So the second energy level has an S sublevel, but it also has a P sublevel. The P sublevel is made up of 3 orbitals, each containing 2 electrons. So that's 6 electrons total that will fit in the P sublevel. The second energy level has both an S sublevel and a P sublevel. So if I add that together, 2 electrons and 6 electrons, I get a total of 8 electrons. So 8 electrons fit on the second energy level. The third energy level has an S sublevel, a P sublevel, but it also has a D sublevel. The D sublevel has 1, 2, 3, 4, 5 orbitals. If each holds a max of 2 electrons, then that's 10 electrons that will fit in the D sublevel. So the third energy level has S, P, and D. So if we add that together, 2, 6, and 10 makes a total of 18 electrons that will fit on the third energy level. The fourth energy level is larger. It has an S sublevel, a P sublevel, a D sublevel, and an F sublevel. The F sublevel has 7 orbitals. Each will hold a maximum of 2 electrons. So that's 14 electrons that will fit in the F sublevel. So if the fourth energy level has an S, P, D, and F sublevel, then I add together 2, 6, 10, and 14, and I get a total of 32 electrons. So 32 electrons are going to fit on that fourth energy level. So this kind of explains why we see the numbers we see. for each energy level. It's because we keep increasing the number of sublevels that exist within each energy level. What we have to do with this information is, rather than just put dots on a Bohr diagram, we have to be able to write an electron configuration. So an electron configuration describes the probable location of the electrons in the electron cloud. Okay, there are several rules we have to follow whenever we are writing an electron configuration and placing electrons in the electron cloud. So the first is the Aufbau Principle, which you've probably gone over before. The Aufbau Principle simply says we have to fill it up from low to high. We have to start with the 1s level and fill that up before we can go to the second energy level, and then fill that up before we go to the third. So low energy levels must fill up completely before electrons may occupy higher energy levels. So looking at this chart, we're going to start at the bottom with the lowest amount of energy. We're going to fill up the 1s sublevel. And from there, we're going to work our way up. Okay, that's the Aufbau Principle. Hund's rule says that every orbital in a sublevel is occupied by a single electron before any orbital is double occupied. So over to the side, I'm going to show you what I mean. Notice that the 2p sublevel has 3 spaces. That's because a p sublevel has 3 orbitals. Now, electrons are represented using arrows. So when we're drawing out these diagrams, we're going to use arrows to show the electrons. If I look at a p sublevel, it has 3 orbitals. What I'm going to do is I'm going to fill it up with a single arrow in each space, representing a single electron in each orbital, before I go back and double up. What I'm not going to do is I'm not going to just start doubling up right away. Okay, so this would be correct. We have to spread it out and put 1 in each orbital before we go back and double up. We're not going to just start doubling up right away, because then we end up with empty orbitals when they don't need to be empty. They need to be spread out. The third rule is called the Pauli exclusion principle. So no 2 electrons may occupy the same orbital with the same spin. So this is called the up-down rule. Okay, up-down is good, up-up is bad. Okay, the reason is electrons are negative. They have the exact same charge. That means that they repel each other. So if one of them is spinning in this direction, the other one is going to be repelled and spin in the opposite direction. Now, instead of showing curvy arrows spinning in opposite directions, we show an up arrow and a down arrow, still going in opposite directions. What we should not see in the diagram is 2 up arrows or 2 down arrows in the same space. Okay? So this chart right here is known as an orbital diagram. And we're going to complete this orbital diagram for the element gold, which is number 79 on the periodic table. That's significant because if it's number 79, it has 79 protons. And if it's a neutral atom, it also has 79 electrons. Okay, remember that the atomic number tells us the number of protons and the number of electrons for a neutral atom. That means we're going to have to put 79 arrows in this diagram. But we're going to follow the rules, and we're going to start at the bottom. We're going to fill up the 1s, up, down. I'm going to fill up the 2s, up, down. I'm going to fill up the 2p, up, 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 down, down, down. Now that's 10 arrows so far. I need a total of 79, so I'm going to keep going. Up, down, the 3s fills up. Then next I see the 3p, up, 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 down, down, down. And if I look at this in terms of increasing energy, the next level to fill up is going to be the 4s sublevel. That's actually going to fill up before we finish filling the third energy level. The reason is the 4s requires less energy to fill than the 3d sublevel. So I'm going to go ahead and put 2 arrows in the 4s orbital and then start filling up the 3d sublevel. Then I fill up the 4p. Then the 5s. And then if I look at it, before I fill up the 5p, I'm going to fill up the 4d. And I'm still not done yet because we need a total of 79 electrons. So I'm going to keep going. 5p fills up next. Then the 6s. And then if we look over here, the next lowest energy level, the next lowest energy sublevel is going to be the 4f sublevel. So I'm going to fill that one up. With 14. And that gives me a total of 70 electrons so far. We've drawn 70 arrows, okay? So if I need 79 total, I need 9 more. I'm going to go to the 5d sublevel. And actually, I'm not going to draw that 10th arrow. And the reason is I only need 79. If I draw 80, then I'm actually drawing the orbital diagram for Mercury because that's number 80, okay? So I'm going to stop there. I'm not going to draw that last one. It should just be blank. And this is my complete orbital diagram. It shows me the probable location of every electron, but it's not really fun to draw all those arrows. So there is a shorter way to do that, and that is electron configuration. So what we can do is we can just write out what levels filled up in what order with how many electrons. And I'm going to start the same way I did with the arrows. I'm going to start at the bottom. So we filled up the 1s sublevel with 2 electrons. Then we filled up the 2s sublevel with 2 electrons. And then the 2p sublevel with 6. Then the 3s filled up. The 3p filled up with 6. Then we filled up 4s with 2. We filled up the 3d sublevel with 10. 4p, 6. 5s, 2. 4d, 10. 5p, 6. 6s, 2. 4f, 14. And 5d, 9. Now, just like all of our arrows should add up to 79, all of the little exponents in our electron configuration should also add up to 79. So if you add up all these little exponents right here, those should add up to 79 to show us the 79 electrons in the electron cloud for gold. And you might be thinking, how am I supposed to remember what order these fill up in? How do I know what fills up next? How do I know that it goes 5s, 4d, 5p? Well, the periodic table actually helps a lot with this, okay? Okay. So the electron configuration is written in the order that the periodic table fills up. Okay. So each period, which is a row, okay, going across, represents a different energy level. So down here you have this blank periodic table. There are only 2 elements on that first row, that first period going across. That represents the first energy level and the 2 electrons that are there. Once that's full, you have to go to the next one, the second energy level. That one has 8 elements across. And once that's filled up, then we go to the third energy level, 4th, 5th, 6th, and 7th. Okay? Now each block represents a different sublevel. Okay? So you just need to follow the periodic table in order to write an electron configuration. So, for example, we just wrote the electron configuration for gold. I'm going to move my notes. Okay. Here is the periodic table. Okay. Let's think about how we just filled this up. We started, remember, gold is right here. Okay. Gold is number 79 on the periodic table. The first thing we did was fill up the first energy level, the first sublevel, with 2 electrons. Then we filled up the second sublevel with 2 electrons. Then we filled up the 2p sublevel with 6 electrons. Notice that this section of the periodic table, this block, is 1, 2, 3, 4, 5, 6 elements wide. That represents the 6 electrons that fit in the 2p sublevel. Once that fills up, we have to start putting electrons on the third energy level. So this is the 3s level, and it only fits 2 electrons, so it's 2 elements wide. And then we filled up the 3p sublevel with 6 electrons. And then we filled up the 4s sublevel because it actually took less energy to fill that up than it did the 3d sublevel. The 3d sublevel is actually on the 4th row, the 4th period of the periodic table, but it's part of the 3rd energy level. And notice that this middle section of the periodic table is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements wide because 10 electrons fit in the d sublevel. Then we have the 4p sublevel, 5s, 4d, 5p, 6s, and then after we filled up the 6s sublevel, we actually started filling up the 4f sublevel. So if you notice, this bottom part of the periodic table, the lanthanide and actinide series, is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 elements wide. So this block represents the F sublevel, okay? After the F sublevel filled up, then we had the 5D sublevel. And if you notice, gold is the 1, 2, 3, 4, 5, 6, 7, 8, 9th element in this row right here. So 5D, 9 is its electron configuration. That last part of the electron configuration works like an address. So you should be able to find your element. This is 5D, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? Now after that is the 6P, 7S, 5F, and 6D sublevels. And that's as far as we go. Okay? So just like I was saying before, each period represents a different energy level, but each block, this is called the S block, this is called the P block, this is the D block, and this is the F block down here. And actually this one would be part of the S block, okay? This should help you write your electron configuration, okay? So take a second, pause, stop the video, and I want you guys to try this example. I'll post a second video that has the answer.